Hi, this is Sean Collins, and this is tutorial 5. It's a focus on chronic heart failure, cardiopulmonary responses, if they have a disease-specific impairment causing their endurance limitation. So, this is where we are in the tutorials. We've come quite far. If you're confused about any of these issues, I suggest you try going back, maybe talk to colleagues. Worst case scenario, you might have to communicate with me and let me know where I've gone terribly, terribly wrong in trying to make these ideas clear, and I can try it again. But you also should feel free to email me. My email is Sean_Collins@uml.edu. Okay. So to take us back into the algorithm, we're sort of hanging out here in the meat of the algorithm still. This point here, this sort of major break point, which, if you remember from the quadrants, really determines the right versus left column on the table, whether or not somebody has a disease-specific impairment that limits their endurance, or whether they do not have a disease-specific impairment that limits their endurance. And we've established that the normal response to the cardiopulmonary system to both steady state and graded exercise is an indication that the individual does not have a disease-specific impairment limiting their endurance. But now we're here to talk about what happens, or what are some indicators, what are the clues that there is a disease-specific impairment limiting someone's endurance. Now, the first thing to say is that having heart failure alone does not mean that this is true. There are lots of individuals with heart failure that this is true. So that's the first thing to say, in case anyone hasn't been to any of my talks and wasn't aware of that. So what we're looking for are the responses that are not normal. And what are they? What is the heart rate response that would be considered not normal? A drop or no change wouldn't be normal. An increase in heart rate is normal with workload. So an increase in heart rate is normal. Now, it is a strong indicator of poor fitness if it is a steep increase, and it is an indicator of fitness or of relative capacity if there's a shallow increase in heart rate. But even in superior athletes, with an increase in workload, there's an increase in heart rate. So even if they have a resting heart rate of 45 beats a minute, when they get up and they walk, it goes up a little bit. So what we can't tell from heart rate is that if there's an increase, we can't determine whether it's a normal or a not normal response. So heart rate increases basically gives us, it only confirms the possibility of a normal response. It doesn't say anything about an abnormal response. However, if there's a drop or no change in heart rate, then it can be an indication of some cardiac pathological process whereby there may be a disease-specific impairment. So a drop in heart rate might be because of some arrhythmia that's leading the heart rate to decrease with activity. No change in heart rate also could be an arrhythmia. If the person has a pacemaker, it may be that the pacer is not properly responding to the normal cues that a rate-responsive pacemaker should respond to. So heart rate is very informative if there's a drop or no change. I could say that if you've increased the metabolic equivalent of at least by at least 1 MET, a 1 MET increase, there should be an increase in heart rate. And if there isn't, if there's no change or if there's a drop, then this is concerning. So I will circle it in red. I will do a separate webinar tutorial purely on METs. But for now, let's just leave it at if there's an increase of at least 1 metabolic equivalent. What's an increase of 1 metabolic equivalent? Supine to standing. Standing to walking. Walking to stair climbing. These are all transitions in activities of daily living that are indicative of that are about a 1 MET increase. Okay. Blood pressure. Let's take it as systolic blood pressure and as diastolic blood pressure. And then we'll take in between the two pulse pressure. Systolic blood pressure should increase. It should increase about 5 to 12 millimeters of mercury per metabolic equivalent. So when someone goes from sitting to walking, there should be an 8 to 20 millimeter of mercury increase in blood pressure, in systolic blood pressure. That's what there should be. Now, the reason we can be more confident about the increases in blood pressure is that one of the ways we adapt to aerobic activity, to exercise, is we increase our cardiac output through a predominance of stroke volume. I had shared with you this equation, cardiac output equals stroke volume times heart rate. I've told you that heart rate is not something we can give how much it should increase. All we can say generally is that it should increase. Whereas with blood pressure, I'm telling you how much it should increase. Well, cardiac output equals BP times total, BP equals cardiac output times total peripheral resistance. So one thing is for sure, if somebody increases their workload, there is a set increase in cardiac output. Now, as we get fit, we rely more on stroke volume, and therefore the heart rate response can be extremely variable between people and even between points in time in people, because the stroke volume varies in its response. But the cardiac output will increase a given amount. So given a certain body size, when you go from sitting to walking, you have a very regular increase in cardiac output. So let's say you have a 10 liter per minute increase in cardiac output. You might at one point increase that by primarily increasing stroke volume. And then you might decondition and then start to increase that by primarily increasing heart rate. But it will be a set increase in cardiac output. Now, blood pressure is related to cardiac output. So blood pressure, therefore, has a fairly regular, required, or highly associated increase in quantity with with increases in metabolic equivalence, increases in workload. That's helpful. That is very helpful. It allows us to say more about blood pressure. It allows us to define poorly responsive blood pressures. So blood pressure that indicates somebody has indications from blood pressure that somebody with heart failure has a disease-specific impairment influencing their endurance are no change, a hypo change would be less than the 5 to 12 per met. So if you only had a 5 millimeter of mercury increase from supine to walking upstairs, that would be a hypo change. And if there's a drop, that is an absolute literal red flag. So drops in blood pressure during increases in metabolic workload are a clear signal that the cardiac pump is not doing what it's supposed to do. Pulse pressure should increase. If pulse pressure stays the same, so pulse pressure, no change or drop. Diastolic blood pressure increases. These are indications that there may be a disease-specific impairment limiting this person with heart failure's capacity. So getting away from heart rate and blood pressure, let's say some other signs of a cardiac disease leading to endurance, cardiac impairment leading to an endurance limitation. Let's say a drop in SpO2 that typically is associated with other signs, such as a drop in BP, no change in systolic BP, for example. Lung crackles on auscultation, altered pulse rhythm. These would be other big signs that somebody is having a cardiac impairment that is leading to their reduction in endurance. So that's going to be it for this tutorial 5. Next we'll be doing tutorial 6, which is specifically focused on the on obstructive lung disease. Thank you.